SwayamPrabha. Digital India. Educated India.
Okay. So, in the last class we have discussed about this chemical kinetics reactions, heterogeneous and homogeneous. We also had a list of the combination of heterogeneity like gas liquid, that is one heterogeneity, or liquid solid, liquid liquid, all that. And we have also listed out taking only one reactor called packed bed reactor, it is a catalytic packed bed reactor. Then we have written some 3-4 different rates for the same reactor, rate of reactions. But is there a connection between these 4 or 5 rates? One can be converted into other rate, they can be easily converted if you look at those equations, but let me write, because it is not obvious to everyone. I cannot only say, see 1 or 2 people who say yes, 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 we know, but all there are other many people who may not know that at all. So, that is why let me write that, and without writing the complete definition, we have written yesterday, yeah, this is equal to 1 minus V I have written, you can correct that one, V epsilon voidage, correct, voids we have told, no. The first definition R1 dashed was based on voids of the bed, okay, packed bed, yes. So, this is dNi by dt, then we also have, yeah, this is volume of particles, other one, right. So, this is again dNi by dt, then we also have, yeah, weight, and the other one is for surface area, dNi by dt, right. So, the common thing here is dNi, right. So, using this particular one, I can now convert one rate into the other. That means, if I know rate based on W, weight of the catalyst, then I can also convert that into per unit surface area, if you know the surface area, of course, you should know that. So, that is why general expressions can be written here. So, now taking this dNi as equal, because dNi, 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 we can write these equations very easily. This is V epsilon Vp W yes. So, for example, if I want to take these two, that means I know based on rate based on W, I would like to find out, yeah, this Ri for strikes, okay. So, then this will be simply this Ri 3 strikes W divided by S, okay. So, that is why one, I know it is a big problem, you may not know now, okay. In fact, yesterday Ranganathan also was telling me about the same thing, because he was trying to have some gasification papers he was reading. Every paper gives a different one, some people give a surface area, some people give a weight of the coal, and some people give on the surface voidage of the bed. So, there are so many things, sir, I think it is very difficult to convert. So, that is why unless you have the clarity here, then you will make a lot of mistakes in defining rate itself, which is the basic parameter for our design expression, okay, that which gives me kinetics, and indirectly that gives me rate of reaction, okay. So, finally, our conclusion is that rate of reaction, already we know, okay, I do not want to write an equation, is a function of concentration and temperature, that is all. These are the two terms you will have. If it is heterogeneous reactions, this concentration term, this term will be a function of both physical kinetics and chemical kinetics. I will again discuss with you once we understand the basic reactors, then we will go to again kinetics, and I will also derive 1 or 2 equations for heterogeneous reactions. Homogeneous reactions can be simplest one, zero order reaction. Okay. What is zero order reaction equation? Yeah, zero order means it is not a function of concentration, actually it is C concentration raised to the power of 0. So, fortunately that has become 1, so that is there only K, right. So, that is the easiest one, simplest one, then first order, but you should now onwards never should think about this order of reaction at all. It can be any reaction rate, like if I am talking about one particular instant, it may be K into Ca divided by some constant, again capital K1 Ca plus Ca square. It can be anything, right, because that is why you cannot have a single idea in your mind that you should have some order of reaction. What is the order of reaction for this? Please remember, order of reaction you can tell only for elementary reactions. Order of reaction we have one, okay, yeah, but you know even empirical order of reactions where you find out sometimes Ca to the power of 1.2, 1.5, that is only possible if you have concentrations only raised to the power of something. Okay. So, it should be only in this form, that is the okay, sorry, rate as some K Ca to the power of A, Cb to the power of B, etc. Right. So, there is a name I have forgotten now that name. So, this is Ca to the power of A, only here you will have rate, but the moment you have something else there like this, you cannot tell about rate. That is why even Michaelis-Menten equation, which is some format like this, correct, no? Some format like this, again you have to specifically say that at very high concentrations, okay, so this K may be neglected, if the concentration, if Ca is 1000, this K is 1, then it becomes 0 order. So, on the other hand, when this constant is very large and this constant is very small, that becomes first order. So, that means unnecessarily you are trying to simplify things and then say that this is the order of reaction, it is not required, right. So, that is why whatever reaction you have here, reaction rate you have here, somehow you have to introduce this in the reactor design expression, that is what we are going to derive, and then integrate that, and sometimes it is possible to integrate analytically, sometimes it is not possible. So, you have to go for graphical integration or numerical integration, and then finally calculate either volume if conversion is known, or either conversion if volume is known. That is all the entire reactor design. Good. So, that is the one. So, now I think this is the, here till now I just wanted to give an idea of what is rate of reaction and then how do you define it. The definition of rate is actually moles per time, but we would like to have that one as an intensive property. So, that means whoever talks, we will talk, all of us together we would like to talk the same language. So, that is why take some parameter, volume of the reaction mixture or weight of the catalyst or volume of slurry, or this volume of slurry means volume of solids plus liquid together, but some base which is uniform for all of us. So, then automatically all rates whoever do it, I mean you may do in IIT Madras or Anna University or somewhere Coimbatore or somewhere Nagpur University, you do same experiment based on the same volume, you should get exactly the same rate. So, that is the reason why that intensive property is very important for us, because all of us talk about the same language. Otherwise, I take in IIT Madras 2 liters, Abdul takes, I think he is there now, currently he is in IIT Madras only, but I think he would have taken in his AC Tech only, okay. So, 5 liters, 5 liters. If you are talking about only moles per time, moles per second, he will have a different value, I will have a different value. But if we normalize that with the volumes which you have taken, I will divide by 1 liter or 2 liters here, and he will divide by 10 liters A and B, then automatically our answer should be same if it is same reaction conducted at the same conditions. So, that is the reason, please remember all this. These are simple things, many people may not teach you or they would have taught you, but you would have never cared, but these simple things also are very important, and do not try to forget the moment you leave the this lecture. okay, that is happy, because why unnecessarily taxing our brain. So, I think only at the time of examination we will see all that, but this is not burden at all, because this is very simple language I am talking. You do not have to really feel or struggle to record the data in your mind. What is there to struggle? I think very simply I am trying to explain. Okay, good, very nice. So, now we will go to contacting. This contacting will give us what kind of reactor we are talking about, and we are talking about ideal reactors. Non-idealities, you see, ideal behavior of human being anywhere in the world on this planet, we do not know. This ideal behavior in some other planet may be different. Okay, we should not harm people. There may be the law, I mean the other planet, it may be only the law that okay, you should harm everyone. We do not know, I mean what kind of life they have, and we only have what is called life based on carbon. If you life based on silica or some other element, then the behavior may be totally different. I do not know whether you have seen some old movies, that is why you have to see movies, I say, and also observe the science in that. There were movies called Aliens. I do not know whether you have seen, saw it? Yeah, I think he is my friend. I think most of the movies which I see, he is telling yes. Yeah, see, this alien does not have blood, it has only highly concentrated acid. Okay, if some small, the spaceship goes there, and then the alien enters and they try to kill. The moment they started, one limb will cut, and afterwards highly concentrated acid will ooze out from the body. Then that concentration, it is so concentrated, the flight, the spacecraft has some 3-4 stairs, okay, and then through all that it puts the holes and then goes down. That much concentrated, and it falls also on one person. I think immediately his face will become almost dissolved, and then he dies. So, that is the kind of thing. That means the planet, on that planet life is developed in that way. So, that is why at least on our planet, when you talk about good people, we should not harm others, we should try to help. You take any religion, these are the only things every religion tells. That is why I do not have a religion, because all religions are same. Everyone tells the same thing, do not harm anyone, do not try to help. What else you have? Be good to others. That means all same thing only I am telling many times. Okay? So, like that means it is very simple to identify good people with these 3 rules: easy, helping, good. Right? That is all, only one rule. That is exactly the same reason why also we would like to assume ideal reactor. Because if I have something ideal in my mind, it is very easy for me to remember. That is the most ideal case. Non-ideality means, to deal with non-ideal people, it is very difficult. We do not know when he will get angry, when he will harm you, when he will come and just stab you back. So, all these things, why so many problem? If all of us are good, then absolutely there is no problem on this planet. You need not fear about anyone, and then things will be very happy. You do your thing and they do their thing, and it is excellent. So, that is the reason why we first think about contacting, ideal contacting, where we have some definitions for ideal reactors. So, these ideal reactors happen to be in chemical engineering only 2, and that is batch and continuous reactors. And in continuous reactors again we have plug flow and mixed flow. Okay? These are again 2 extremes, and this is one where there is no continuous feeding and continuous removal of the product. You just put all the things in the reactor and wait for some time. That time is now you have to calculate from the design expression, and then after that time discharge and then pack it and then send it if it is pure product. Otherwise, you have to send it to distillation column, absorption column, or whatever. Okay? So, that is what is the one for ideal batch reactor. And now the first question I would like to ask you is, when do you choose a batch system and when do you choose a continuous system? Do you have any rules for choosing continuous system? And for example, after MTech or after PhD you got a job in
batches generally.
flow rates?
For slow rates we choose
For slow
reaction rates.
For slow reaction rates, you choose what?
Batch reactors.
Why?
It will.
Yeah, you have to also answer though. Yeah, because
it will take
continuous
reactor, it will occupy more volume.
No, you tell me in terms of batch reactor.
No, if you take continuous reactor.
Yeah, no, I will come one by one. Yeah.
Yeah, if you take continuous reactor, it will take more volume in terms of batch reactor?
Why you should take more?
To provide
When
high
you
Yeah,
have,
Abdul.
when we want to
Yeah, we will discuss. Everything will be clear later.
In a batch reactor, say we can produce many chemicals. It can be seasonal chemicals. But in a continuous reactor, we use it for specific.
So you are asking for flexibility.
Flexibility is there, and one batch reactor we mostly go for a small output, that is a small quantity. Whereas continuous reactors gives us higher quantity we can use.
Okay. Yeah. Okay.
പക്ഷേ ഔട്ട്പുട്ട്സ്
Totally wrong concept.
ബാച്ച് ആവുമ്പോൾ
Totally wrong concept, because when you want to increase conversion means what? I mean, we can only reach 100%, right?
Yeah, in batch, some reaction in batch is very low conversion, having a very low conversion. Say for example, if you want to make...
You can wait for long, I mean, you are from industry? Yeah, okay. Yeah, you can wait for very, very long time and then still you get 100%
Time is
conversion.
the variance, I mean, in batch reaction...
But here we are not discussing about time, because a batch reactor cannot give more conversion when compared to any other reactor, or less conversion. Because all reactors, if you wait sufficient time, you may get 100% conversion or equilibrium conversion, because 100% conversion is not possible for all the reactions. If it is equilibrium reactions, reversible reactions, then maybe 60% is the maximum. Afterwards, what will happen to the rate? Yeah, zero. And then when you are designing the reactor, you need again infinity when you reach zero, because minus RA will come in the denominator. That is the reason why you cannot. Right? Okay. Anyway, I think that's not correct. Last time you see, here we are only discussing about, we are not talking about the timings. We are talking about there are 3 ideal reactors, and I mean, of course, first batch and continuous, 2 systems. Where I am just asking a question: when do you use a batch system, when do you use a continuous system? Okay, that means if you take batch, in between you have to stop and again wait. That time is lost in the production. So that is why if you have the continuous system, so then continuously you feed and continuously you get all large scale productions, like for example ammonia, sulfuric acid, nitric acid, HCl, all these heavy chemicals what we call. Okay, so large amount you produce. So for those things the best design is only continuous design. Okay, small production rates normally pharmaceuticals. I mean you won't produce millions and millions of tons of headache tablets. Okay, as one of the drugs. So like that, because it depends on, because everyone is not getting headache. Someone may get stomach ache, someone may get headache. Okay, so if for every disease, if you have only one medicine, that is excellent, that is poison. Okay. Okay. Anyway, so that is why I think pharmaceuticals, for example paints. Okay, but like that, depending on the season, depending on the demand, you can have the flexibility in batch system. That is the main criteria. That is why pharmaceuticals, food industries, pesticides, herbicides, all these industries, if you go and look, I think even this penicillin and all that, pharmaceutical industries, all these industries will have only batch systems. But you may see one particular factory where continuous system is used even in pharmaceuticals, but there must be a specific reason, because they want to produce very large quantities, or they would like to have very good control. Advantage of using a continuous system is you will have a good control, because it is flowing. If the flow rates are fixed, nothing is going to change. But whereas in batch system, every time you are feeding, every time you are discharging, then you are starting. Okay, and also batch system, is it unsteady state system or is it steady state system? Batch system. Intrinsically, all batch systems are transient systems, unsteady state. So during unsteady state, you will not get uniform product. Of course, in batch reactor, if you use good mixing and all that, you will get it. But anyway, there is some uncertainty. Whereas in continuous systems, once you design, you will get beautifully with the steady state and also the steady product within plus or minus some small range. Which industry you worked? Which industry you worked? Huh? Oh, what are they producing?
They are producing baby powders.
Oh, okay. Are there chemical reactions or chemical reactors?
So I was in contact to the previous company I was. Before that I was working with some chemical company.
That company you are talking. What were they producing?
Potassium metal.
Potassium?
Metal.
Okay. So yeah, please. I mean, what is the production rate?
Production rate is actually 900 kg something.
That is nothing. For a chemical company, that is nothing. So that's why probably they are going for
Batch.
yeah. What is the reaction?
Reaction is sodium metal plus KCl.
Yeah,
It will be melted.
that is in solid, and this is yeah, melted. You know,
90 centigrade.
that is gas liquid reaction, which is normally very slow. Okay, and I think one answer was there what he told. What is your name?
Rahul.
Rahul, your name?
Manigan.
Medicanton. Okay, yeah. Rahul, what you said, that one point is right. If the reactions also rates are very slow, then we will go to batch systems. The reason is, it is not the volume and all that. You can give whatever amount of time that is required in a batch system. Simply, you know, if I don't allow you to go out of this room, whole day I can arrest you here and then talk CRE. Okay? So really, no, that's all. That's why you have that time to keep the material till the reaction is over. Because it is slow, it takes more time. So in batch reactor, you can provide that much time. Similarly, of course, in continuous reactors also you can provide. The length will be very large. Okay? Yeah. And you can also provide the same thing in a mixed flow reactor. Correct? No, mixed flow reactor, if you cut off both limbs, it is only batch. Both limbs means entering, leaving. Cut both, then it becomes, because there is also stirring, right? Then automatically that becomes. So we will see which is efficient, which is not efficient, why and all that. Okay? Efficient in the sense that for a given volume, which will give you more conversion, or for a given conversion, which will give you less volume here. Less volume is our criteria for a given conversion, and more conversion for a given volume. Those are the main objectives of the entire reactor design. Okay, good. So that is why batch system and continuous system, you know now how to choose. Okay, but normally if I want to give the names, I mean not names, the numerical values for how large, I can tell you definitely 1000 tons per day, you will go for only continuous. Okay, but I have a problem to tell that, you know, 10 tons, 50 tons, what do you use? There economics will come into picture, design will come into picture. You have to calculate separately for continuous system, you have to calculate separately for batch system, compare the economics, then your labor and all that will come into picture there. Because in between someone has to discharge all that criteria. All that you take and then now decide which side you are in. It may be economical if you go for batch, or it may be economical if you go for continuous. This is the grey region where we cannot tell. But definitely, as he said, you know, 900 kg, 99% of the time we go for only batch system, right? Yeah. So that is how you can say that, okay, around 1 ton or less, definitely we can go for easily batch systems, or 100 and above per day, again you can go for continuous. But in between somewhere you have to check the economics and decide which reactor is the best. That is why we have the computers now. Calculating power is very high. So just you know Excel you can use for finding out Excel sheet. There is a program where you can use automatically. If you change one, everything will change. One parameter you change, all the other things will change, and finally your parameter in the last column is either conversion if volume is known, or volume if conversion is known. See how the volumes are changing or conversions are changing given the other one. Okay? So that way you can try to simulate and then try to find out which one is the best system, right? But general thumb rule is, for low production rates, flexibility in production rates and very slow reactions, batch reactor is used, and continuous reactor is used for very high production rates and also good quality. And which one will be costly? Initial cost. Continuous, definitely, because it needs more instrumentation, all that. But still we go for that, because that is why you have done your project, right, by taking depreciation cost and also break even. Yeah, break even, all that you calculate. The break even should be as quickly as possible. So that is why after calculating, after designing the reactor and also taking all other components, all other equipment, then you have to again calculate using your economics, then finally say break even point. Break even point cannot take 100 years. Okay, it should be as short as possible. If you are able to make the system as short as possible, then your profits start coming for you, right? So that is the overall picture of this batch and continuous systems. Okay, good. So now in continuous, now we have two again, plug flow and mixed flow. Let me write that, I think, for the sake of others who do not know about this. Plug flow and mixed flow. Okay. So, this plug flow is normally tubular reactors. Okay. So, it can have of course any length depending on the system. It comes out. Okay. That is plug flow. And mixed flow, generally you will have tank reactors where it is continuously entering and continuously leaving. As I told you, if I cut off these two, then that will be nothing but batch reactor. Okay. So, we are supposed to use plug flow reactor and mixed flow reactor. I am hesitating to ask the question because I have not explained what is plug flow, what is mixed flow. I do not know how to give that answer, because you have exposed to two courses earlier in your BTech and MTech. So, that is why I am now asking this question. Okay. So, given a chance to you in the continuous system you have chosen. Now, there are two alternatives. So, you got job in some industry and then your boss asks, okay, now choose the reactor. Okay, good. Yeah. So, I think of course, I have not told many complicated things yet, but I think only simple things only we are discussing, right. Yeah, anyone? I think when can you choose plug flow reactor, when can you choose mixed flow reactor?
Plug flow reactor.
Why?
Pressure we need.
Pressure?
High pressure we need.
Why high pressure? There are many reactions without much pressure also. There are many gas phase reactions occurring at only 1 atmospheric pressure, normal pressure. High pressure is not the criteria.
If we do not want the concentration to fall down rapidly,
Why you don't want concentration to fall rapidly? We want, because when concentration is falling rapidly, rate of reaction is high. When rate of reaction is high, time is very small and then I will get very small volume. No, please tell, please tell your mind, because these are the misconceptions in the mind that you should not keep them. That is why I told cobwebs there, you have to remove them. So, that is why please, without any fear, please talk if you have anything. And also, it is worse to have a wrong answer than not having any answer. If you do not have any answer in your mind, that is very bad after 2 courses of CRE. But even if you have wrong answer, no problem. So, that is why you have to tell something. Very Jahanavi.
Flow occupies more volume than plug flow.
Again, repeat.
For a particular conversion, the mixed flow has more, it occupies more volume than plug flow, so we prefer plug
So
flow.
higher conversion.
For all reactions. Yeah, then as you said, always mixed flow will give you more volume. So, that means always we should take only plug flow, but we do not do that. We also use mixed flow, we also use plug flow. That means there is a choice left. No, this is the problem. Do not worry, you are in the good company of our brothers and sisters. Okay, in this course reactor theory, I am again starting all the basics. The reason is, for this also no one gave the answer, and even for batch and continuous also many people do not know the answer. When do you choose batch system, when do you choose continuous system? Now I think at least you know. And please remember, only this kind of questions only are asked in the interviews. No one will ask you very complicated mathematical equation in the interview. They start only with these basic things. Okay, what is a reactor? That is why the questions which I gave, they are very simple and very nice questions for in terms of Gopi's language, general knowledge. General knowledge in CRE. Okay, that is what is the first. I think you would have definitely attended some interviews before coming here. Okay, anyone asked you what is the dispersion equation to write? If he has asked you, really he does not know how to interview. Really, no one will suddenly start and then ask dispersion equations. They will start slowly. Okay, what is reactor, and then what is plug flow reactor? In plug flow reactor, is there dispersion? Now you tell me what is dispersion equation. So many steps are required. Okay, so that is why even this question also, when do you choose plug flow, when do you choose mixed flow? is many people cannot, not able to answer. One answer was there. Who said gas phase reactions? Oh, you said gas phase reaction. That is right. Not easy pumping. The gas phase reactions, the reaction time is very, very small. Most of the time it happens within minutes. If you calculate ammonia residence time in that reactor, or SO2 to SO3 residence time in that reactor, or any gas phase reaction, there are many gas phase reactions. The rate of reaction is so fast for gas phase reaction, because molecules are easily moving, they are colliding, and so easily rate of reaction can occur. So when the reaction time is very less, we choose plug flow reactor because it is very easy to provide short residence times in a plug flow. Okay, why? It is a pipe, right? And of course, because already you know what is plug flow, right? Yeah. In terms of Reynolds number, can you tell me under what Reynolds numbers you can say that you have plug flow? The value of the Reynolds numbers. Good. Okay. Now I will try to give the answer in indirect way. You know fluid mechanics, right? Okay. Now I will draw the laminar flow velocity profile. Okay. So this is the pipe. Yeah. How I have to draw the laminar flow velocity profile? Parabolic. Okay. Okay. That is the one. And turbulent. This is only fluid mechanics knowledge what we are using. Now turbulent. Okay. I have Reynolds number maybe 40,000. What kind of profile I get? Yeah. So it is not still flat.
Initially boundary, yeah.
Like this. Okay. Good. So what is that you have written the answer in your first examination, that the definition of plug flow? Those who have written, those who have not written, I think it's okay. It is, theoretically speaking, the Reynolds number should be equal to infinity. Very good, Merit. Infinity. Then only you will get ideal plug flow, what you call, with flat velocity profile. Otherwise, whatever Reynolds numbers you use, maybe 70,000 if I go, what will happen? It may be like this. As long as you have the walls, still you will have some molecules clinging to the wall, and then you will have zero velocity profile there. From 0 to flat velocity, there must be some continuity, right? It suddenly cannot jump. So that is the reason why theoretically speaking R equal to infinity for this profile. Okay? Yeah.
So the mixture flow, the turbidity should be more high than for the plug flow. Should be.
Oh, what is that?
So in a mixture flow reactor, the turbulence should be will be higher than the plug flow reactor.
Yeah, by definition of mixing, I think you should have infinite mixing there. Yeah, infinite turbulence.
So, but then in plug flow also we have some sort of mixing.
Where is mixing?
So, but the molecules somehow mix with each other.
No, I think that I will explain when you come to definition of plug flow. Okay, yeah, I think all these concepts are there, I know. That's why I think I have to again teach all these things. Okay, now we are only talking about plug flow and mixed flow. I am now, how do you choose? So that is the reason why I have given this example, Reynolds number. Reynolds number is a form of velocity, right? You should have fixed for a fixed liquid, that means properties rho and the diameter. Then only as you are increasing velocity, you are increasing the Reynolds number. Okay, as velocity is increasing, what will happen to the residence time? Residence time is defined as this length divided by velocity, right? So I told you, I think as when you said gas phase reactions are because of the low residence time required for the gas phase reactions, we go for plug flow. The reason is when you want to maintain plug flow, you need very high Reynolds numbers, right? Okay, not theoretically you cannot go to infinity, but you need very high to maintain that plug flow, ideal plug flow. So that means you should use very high velocities, and if the reaction time is 10 hours, then what is the length of the pipe you require? 10 hours. There are many reactions with 10 hours, and 10 hours no gas phase reaction is there, it is only 10 seconds, 10 hours liquid phase. Okay. So, that means if I am taking a liquid phase reaction where the time required is 10 hours for the reaction, if I want to provide 10 hours in a pipe with velocities almost I mean reaching infinite velocities, because plug flow, you have to maintain plug flow, otherwise you cannot call it is a plug flow reactor if you do not maintain. So, you have to go to very high velocities, then you need a pipe which will go around the world once, okay? Or if it is not enough, it has to go to moon, from there Mars, okay? From here starting from earth. So, that length of reactors you have, but that is why I do not know whether you have seen any plug flow reactor in industry. Most of the industrial plug flow reactors are designed in this fashion. And you know, sometimes in industry you will have 2 kilometers, 3 kilometers length of plug flow. That means like this many, each one will have 30 feet or 40 feet length. Okay. Like that you can now count how many numbers you have to put and then join at these ends, and you can guarantee that there will not be a plug flow, even though we say that it is plug flow reactor. That is why you have non-ideality coming there. Okay. So, the ideal plug flow is only existing when you have velocity equal to infinity. That means you cannot provide even 0 second, correct? No, infinity L by U, this U equal to U equal to infinity, then it becomes 0, and with 0 reactions, I think 0 time, if some reaction is happening, you do not need any reactor at all. You simply do not need any reactor, because even before you mix them, if they are reacting, why do you need a reactor? You do not need anything there. So, that is why you have to choose the plug flow reactor for residence times which are very small, and most of the time that happens only for gas phase reactions. And if there are some liquid phase reactions whose reaction times are very small, there also you can go, but criteria is time. That is one thing. Okay. Next one is, when do you choose mixed flow reactor? Opposite of that. That means whenever you want large amounts of residence times, 10 hours, 20 hours, because it is a tank, it is a tank reactor. So, then you can definitely provide that much time, right? Again we have an equation, we do not know who told you that, tau equal to volume by volumetric flow rate. This is volumetric flow rate, this is volumetric flow rate, okay? This is volumetric flow rate. I want to provide 2 years residence time, 2 years, okay? Exaggerating to just make a point, that is all. So, I can still provide that in that reactor. I may take, let us say, 1 meter cube, and I want 2 years residence time. Can I provide? Is it in my hands? How? Cut off the outlet, it becomes batch. That is all. Drop by drop I will add. Then I can provide not only 2 years, 10 years residence time also. 2 years I told that because your MTech time. Okay. I know you would have seen that big wastewater treatment plants. Why do they need that big size? Have you ever thought? Because of exactly the same reason. The residence time required for wastewater treatment is 3 weeks, 4 weeks, 5 weeks. Okay. That is why, and also depending on the effluent, sometimes they will have, my God, big swimming pools, 5 or 6 together. This goes from there, this goes from there, this goes, that is tanks in series. Okay. Because the liquid phase reaction there, it is very slow. On the top of it, they are all microorganisms. They are also as lazy as us. Okay. They won't work properly. If the temperature is very hot, they will sleep. Like, but we will put AC and then we will sleep. Okay. But microorganisms, if the food is not good, what do you do? If 2 days, I think if the mess is closed, you never come to the class. You take rest. Same thing, microorganisms also like us, because we are also part of this planet, and microorganisms also part of this planet, life wise. So, our behavior is same. So, give them, that is why you put very good nutrients in biochemical reactions, right? And also you give correct condition, okay, 30 degrees, exactly maintain 30 degrees. Like we are maintaining in our rooms, for our body comfortability is 25 degrees. Okay. So, that is why AC and all that we use. So, exactly these microorganisms also like us, and if you make them anger by not giving food or by heating it, because if the sun is very hot, they will say that okay, Chodo, I think you will just sleep for some time and then come in the afternoon. So, all this we have to take into account. That is why biochemical reactions are very, very slow, because exactly like us, but the molecules are different, chemical molecules. They do not behave like microorganisms. Fortunately, these molecules, they do not have life, they can't think. Given a chance, they will go and react. That is all what they know. So, increase the temperature, more vigorously they go, they will not go for AC. So, they will go for more and more collisions and more reaction, because you are giving them more energy, that means more food by giving the temperature. So, that is why as you increase the temperature, the rate of reaction is very, very fast in the actual chemical reactions, whereas up till some point, maybe 25 to 30, in many biochemical reactions it increases. Afterwards, Savita, if you go to 40, it starts decreasing. Not for many, but there are specially designed by God, specially designed microorganisms where even at 60, 70, 80 degrees also they are surviving. Hot springs, sulfur eating and all that, those things. That is fine, that is only few. But those are designed only for some specific purposes. The other organisms have been designed for some other purposes. Okay? So, that is why biochemical reactions is one of the examples where always they go for tank, either batch or mixed flow. Plug flow reactors are very rarely used. Yeah, you can use, provided that no, you can use provided that tube length is one diameter of the earth. Earth diameter, yeah. The length of not diameter, sorry, yeah. The length of the reactor will be one around, one circumference of earth. What is the earth diameter? we have a Encyclopedia Britannica.
327 kilometers.
Excellent. I think we have to clap for him. Very good. So, that multiplied by pi. Which is diameter or radius you get?
Radius.
Oh, radius. You see that 2 pi d, that 2 pi r.
CSR tank volume is also very big in comparison. If we use plug
You
flow,
can
then
use
it's
multiple.
very-
Yeah, but the length there the diameter is fixed most of the time. Okay, you cannot go to so big diameter in plug flow. Okay, what is the diameter you can guess in any plug flow reactors? Diameter. Huh?
Max.
In terms of centimeters or inches. 5 centimeters, 15 centimeters. Yeah. Any other value?
1 inch is diameter.
15 centimeters.
50.
5 is 2 inches.
2 inches.
Oh, centimeters you said.
Length
Oh,
of diameter.
that is half meter.
The other day you showed
50 centimeters is half meter.
chamber process.
That is packet. Not plug flow,
inches
not tubular.
2 inches.
That is packet.
5 centimeter.
Okay. Packet by diameter also. I will come to that also. There are many things to learn here. What you are saying is right. But I think why we are calling that also as a packet, as a plug flow, I will explain to you later. That diameter, big diameter. Yeah. So, that is the reason why most of the time we won't go beyond 6 inches or 8 inches maximum. 8 inches means 200 mm, 20 centimeters or 15 centimeters. Most of you told 15 centimeters. So, that is fixed. So, then when you are going for plug flow, the velocity required is almost very, very high. So, the residence time is, to provide that much residence time, then you have to, the length will be very, very long. So, that is the reason we do not go. Okay. Her doubt is then why the same thing is happening in the mixed flow also, right? That is correct. What she asked is right. But here I have a flexibility in increasing the diameter and also length.
Gas reaction in CSTR.
You can do.
Residence time is less, so
You can do it. Okay. Theoretically you can do it, but no one will do it. Okay. Why? The reason is that the concentration of gas inside that will be very, very less, diluted. Unless otherwise you go for very high pressures in the CSTR. High pressures, you can go to very high, 100 atmospheres, 200 atmospheres. then concentration is Pa by RT. As partial pressure is, if it is a pure reactant, then you will have the total pressure itself is that one. So, that pressure by RT will give you the concentration, but at room temperature if you calculate that concentration, that will be very small. As concentration is very small, you have rate of reaction very small, and then you will again take more time. So, that is the reason why you do not go for most of the time, but we use mixed flow CSTRs in the laboratory to find out kinetics for gas phase also, for kinetics, because you are using a small reactor and then small amount of gas at different pressures or at atmospheric pressure, and you just find out what is entering, what is leaving, perfect mixing is there, then you can calculate what is the rate of reaction for gas phase reactions. Okay. Homogeneous only we are talking here when I am talking about these two reactions, I mean these two reactors. So, now at least you have an idea when do you choose plug flow. Plug flow is chosen when you have the reaction times are very small. So, most of the time gas phase reactions will have small residence times required. So, gas phase reactions is one answer, and liquid phase reactions most of the time we conduct in. Then I will ask another question, what will happen, which reactor is the best if I have highly exothermic reactions? Is it mixed flow reactor or is it plug flow reactor? Your question also there is valid, I am not saying that whether you have gas phase or liquid phase. Gas phase also may be very high exothermic, highly exothermic. Okay, either exothermic, either liquid or gas phase. Which reactor is preferred and why? Plug flow reactor is preferred for highly exothermic reactions. Okay. Mixed flow. Why mixed flow?
Temperature control. Plug flow can also maintain. Heat change can be.
Isothermal is maintained.
Yeah, you have to put only jacket around this. Okay, which is sorry, this one is going inside. Oh, here, so this enters coolant enters and coolant comes out there. Savita, you are telling something? This exchange is never perfect. You can never maintain isothermal condition in a plug flow reactor and you will have what are called hot spots. Okay, that is why plug flow reactor is a lousy reactor for heat exchange. Remember that, really lousy. You can never have uniform temperature throughout. You can have theoretically in your mind, okay, if you have infinite number of heat exchangers. So, that means I will put here one heat exchanger, here one heat exchanger, here one heat exchanger. So, almost every I do not know 1 mm, 2 mm, one heat exchanger if you put, probably you may get almost isothermal. And will you design so many heat exchangers, so many feeds, so many outlets, so many pumps? No one will do. Okay? So, that is the reason why whenever you have exothermic reactions, we go for only, even for very high exothermic reactions, gas phase reactions, because there I do not worry about the timing, I do not worry about conversion, I worry about the heat, where heat may explode after some time if the heat is building up, or when the hot spot is reaching, it may reach the flash point and then everything may burn. So, safety is very important. That is correct, no? Definitely safety is very important. So, that is the reason why even gas phase I have to go sometimes for mixed flow reactors if it is continuous, if it is highly exothermic. So, these are the main two criteria for choosing between plug flow reactor and mixed flow reactor. Now, can you repeat, when do you choose mixed flow reactor? When temperature control is required and when large residence times, that is all. Okay. Any other criteria? There is no other criteria except this. So, that is why when you go for sorry,
problems like clogging and plugging.
Why it is a, when do you get a clogging problem? I have the gas phase reaction, because most of the time gas phase reactions we are using. Okay, plug flow. When do you get clogging? Catalyst particles, when you have that we will discuss later. Okay, when you come to heterogeneous reactions, heterogeneous reactors, that we will discuss. So, it can happen, but whenever you are using even packed bed reactors, a gas phase clogging is very rare unless you design your catalyst loosely. I told you, no, you may go for large surface area, but what you do, you will only finally get only powder if you want to use very large surface area. So there powder may form, that powder may be transported from one place to the other place and then may block. Okay? So those are the problems which you have to separately deal with when you are talking about catalyst design, right. So that is why these two are the criteria which normally we take for choosing between continuous and batch, you know how to choose, and also in continuous between plug flow and mixing flow, when do you choose, okay, how do you choose. So I think this is very good information, you should remember, and again, you know, you discuss among yourself, otherwise you will forget very easily.